Hello everybody, welcome to 7-1 Angles and the Unit Circle. Today we are going to define angles, negative angles, reference angles, and coterminal angles, and find them in the coordinate plane. And then we're going to define radians, convert between radians and degrees, and evaluate sine, cosine, and tangent in the unit circle. So at the beginning it's going to be a lot of defining things, a lot of just understanding some of our key terms for trig going forward, and then from there we're going to talk a little bit about radians, and we're going to talk a little bit about how the unit circle works and how that relates to the three trigonometric ratios that you guys already know. All right, so let's start off with angles in the coordinate plane. So first of all, on a coordinate plane, we have an x and a y axis. This isn't anything new. Our initial side of any angle, at least for most angles that we're going to be dealing with, the initial side of every angle is going to simply be the positive side of the x-axis. So this is where our angle is going to start. Now, every time you've had an angle, let's say in geometry or, just anything like that, an angle typically would look something like this. It would be the combination of two rays, right? And you'd have two rays that kind of join at a point, and then the angle is the measurement in degrees of this like internal part here. And that's essentially the same thing we're going to be doing, but because we're going to be dealing with the entire coordinate plane, you can have angles that look like this. And instead of referencing this interior part, it could actually be referencing this entire exterior part, right? So the angle could be one of two of these things. And more often than not, we're going to have angles that are greater than 90 degrees. So we're going to have like longer and wider angles sometimes than maybe what you're used to in geometry. But I think you'll get a hang of that pretty quickly. So, all right, so if our initial side is the x-axis, our terminal side, or in other words, the other side, the end side of our angles, are going to be what are known as the terminal side. And both of those rays are going to form our angle. And in most situations, if we don't have an angle, just like we use x for a lot of things in math, we're going to use this symbol that looks like this, and it's called theta. And theta is going to almost always be a reference to the unknown angle. All right, so let's talk a little bit about the coordinate plane. So the coordinate plane is divided into four quadrants. We have quadrant 1, which is the positive quadrant for both x and y up here. Quadrant 2 is positive for y, but negative for x. Quadrant 3 is negative for both. And quadrant 4 is positive for x, but negative for y. And I don't know if you remember when you did rotations back in geometry, but these were actually the rules that were associated with it. And it's actually kind of neat that goes into effect now. But if you remember which letters are positive and negatives in these quadrants, that'll actually help you going forward quite a bit. Now, when it comes to angles, remember, we're always starting our initial side on this positive x-axis. And then we're going to rotate counterclockwise around from 1 to 2 to 3 to 4. So in other words, if we start here at the x-axis and we go all the way around and end back at the x-axis, we'll have gone an entire circle, which is 360 degrees. And you'll notice here that I've kind of given you some key points here. 90 degrees, as you can see, this forms a 90-degree angle with the x-axis and the top of the y-axis here. This is 90 degrees. If we keep going, the straight line is, of course, 180 degrees. 180 degrees plus another 90 degrees is going to be 270, and then all the way around is 360. So it's important to think of these key, like, distinctive mark-offs as different parts, because if you're trying to identify where an angle that's 220 degrees is, which we're going to do a little bit later, you're going to have to know, okay, well, 220 degrees is more than 180, less than 270, so it's got to be in quadrant 3. All right, so let's actually do that. Let's practice sketching an angle here. And let's start off with 220. Now, what you'll notice is, okay, we start off at 0, it's going to go past 90, past 180, and then it's going to go in between 180 and 270. Right? And we'll talk more about like getting specific with it. But for now, we know that this is going to be located in quadrant 3. And if we want to do a little bit of math here, we know that we're going to have to start off at 180, right? And then we're going to have to figure out, okay, 180 plus what equals 220? Well, in this case, it's 40. So we're going to go 180 degrees. And then once we get to this x-axis here, we're going to go another 40. So remember that how I told you earlier that in geometry we were used to the smaller angles, right? We're not talking about this down here. This is not what we're talking about. We're talking about this whole piece up here. This is the whole angle is this piece. Okay? And it's just more of a reference just to make sure that you guys are keeping that as a frame of mind, the angle isn't always the smaller part. It starts at one part and it ends at another. So, all right, so that would be sketching 220 degrees. All right, it would be 180 plus the 40. And we'll start to talk about reference angles a little more, but understanding this little 40 piece is actually going to be very important going forward. All right, so let's talk about negative angles. So if you remember when we did transformations, there were often that you'd have to reference either counterclockwise or clockwise. Well, it's still technically true. 90% of the time, we're going to be talking about counterclockwise because we're just going to be talking about positive angles, right? In other words, if we start at our initial side and we go towards our terminal side, we're almost always going in a counterclockwise direction because that's what gives us positive angles. So in other words, let's just kind of look at this first one, right? If I go from this initial side to the terminal side up here in the second quadrant, right, this is going to be 90 degrees plus a little bit more. It tells us here that the angle is positive 135 degrees, right? So this is actually a 45 degree angle here, right, from this point. So we have 135 degrees positive, which means that the negative angle, in other words, the big part of the angle, would be negative 225 degrees, because if we went clockwise from here, you'd actually go from quadrant 4 to quadrant 3 back into quadrant 2, right? So the negative angle plus the positive angle will always add up to 360, and they'll always meet at the terminal angle. So it's just like which direction you're going from the initial side. So if we look at this one, all right, our positive angle in this case is all the way around here to quadrant 4 for 315 degrees. And then the negative angle is just this small piece here, which looks more like an angle you're used to, right? But this angle would be negative 45 because it's going counterclockwise. So both of these would be true representations of what this angle is, but we're almost always exclusively going to use the positive angle. I just want to make sure that you're aware that the negative angles can also exist. All right. Now, this is a very important concept here known as reference angles. The reference angle is the angle created by the terminal side of our angle and the x-axis. So if we want to just kind of go back up here and look, right? Actually, let's go back to this one, because remember how I told you that the 40 degree piece is going to be very important? 40 degrees in this case is the reference angle because that's the piece that goes between the x-axis and our terminal side. And the reason why this 40 degrees is important is because every 40 degree reference angle, no matter which quadrant it's in, is going to share a lot of similarities. So if we can understand what the reference angles are, and when we look at a unit circle a little bit later, you'll see this, but if we can understand what these reference angles are, a lot of times we can just know, oh, this is in quadrant 2. I guess my y value is positive, my x value is negative, right? And then the reference angle refers to a specific kind of point. So reference angles are going to be very important going forward, right? So if we look at, here's an example, an angle of 200 degrees would be found in quadrant 3, right? Because it's a little bit more than 180. And it's going to have a reference angle of 20 because that little bit more is actually 20, right? 180 plus 20 is our 200. So 180 would take us to the x-axis. This other little piece here is the 20 degree reference angle. And this 20 degrees, like I said, it's going to be important more in the future, but it's important to understand what these reference angles are. All right, so let's talk about coterminal angles. Now, the term coterminal shares a couple pieces here. So we have co, which means together or share, right? And then we have terminal, which means end. So in other words, these angles are going to share an end, right? So this end piece here, this terminal angle, is going to be shared by, there's going to be different numbers, different values that all will share the same. It'll look the same on paper, but it'll actually be different values. And you'll see what I'm talking about here. So if we have, let's say we have an angle of 225 degrees. We go past 180, and then we go a little bit more down here, right? And this will take us to our terminal side. We went a total of 225. Now, what would happen if we took this angle, and instead of stopping here, we went all the way around, and then we came all the way back another 225. So in other words, a full 360 plus 225. The angle would look exactly the same, but we will have gone around. Imagine if you're on a clock, right? This looks like it's, what, like 6 o'clock, 7 o'clock? Imagine you've gone a full hour and then another time all the way around to the 7, right? That's what we're talking about. So both of those measures, right? In this case, we have the 360 degrees plus the 225, which gives us 585. So 225 and 585 have coterminal ends, right? They are coterminal angles because they share they look the same, right? And they share a reference angle of 45 degrees, right? The only difference is that this one is an entire rotation greater. So these would be known as coterminal angles. And you'll notice back here, right, I put note every negative angle example is also coterminal because positive 315 degrees and negative 45 degrees are both coterminal. They look exactly the same, right? And they will share the terminal side. All right, awesome. So those are most of the new terminology that you need to know, and just understanding exactly how we look at angles, specifically on a coordinate plane. All right, so now let's talk about radians. Radians are the thing that you always put into your calculator, and then you got some weird number, and then your teacher yelled at you to convert it into degrees. Radians is the thing, I don't know if your teacher told you this, but radians, we always used to say, like, we'll use this later, right? You're going to use this next year or in later math. And now we're here, right? We're going to be using radians. And radians essentially are, it's another way of measuring angles. And what it is specifically is 1 radian is when the radius of your circle equals the length of the intercepted arc. So in other words, if we look at this, I put the little formula here for you. The radian measure is the length of the intercepted arc divided by your radius. You don't really need to know that 100%, right? At least at first, you should understand what a radius is, just like you really should understand like what pi is, right? It's it's a specific ratio as well. But a radian is just, it's going to be another way that we measure these angles. And we'll talk about it here in a little bit, but just know that this, just like you can use degrees and there's 360 degrees in a circle, there's also 2 pi in a circle. And we're going to talk about that. So, all right, since the circumference of a circle is 2 pi r, we can divide 2 pi r by our radius, which in this case would just be r, and it's going to give us 2 pi. What this means is that a full rotation, a full circle, in other words, an angle that is 360 degrees, is also an angle that is 2 pi radians, right? It's an equivalent value. All right, so let's just take a quick look at the unit circle. I'm going to provide this in a few of the notes and a few of the videos. I just wanted you to be able to kind of take a look at this here. But if we look at you'll notice some of these values, right? You'll notice it tells you the 0, 90, 180, and 270 degrees. And then you'll also notice some of these degree values, which may ring a little bit of a bell, right? We have a 30, a 60, right? 30, 60, 90, and then we have a 45 and a 90, right? These are still going to be very important points for us. And actually, this is taking a little bit of a step forward, but do you see how the 30 degree here is the square root of 3 over 2, right? Comma 1/2. Well, this is a reference angle of 30, right? 150 would also be a reference angle of 30, right? It's 30 degrees away from the x-axis. And you'll notice if we look at this point, it's negative 3 over 2, or negative square root of 3 over 2, and 1/2 as well, right? So now you'll start to see why these reference angles matter. And we'll do problems with that. So don't worry too much if, you don't need to memorize this chart yet. You will eventually probably need to memorize this. But just for now, understand that these radians and these degrees they all have matching pieces. Like, they're just different ways of measuring the same thing. So what if you have something in radians and you need to turn it into degrees, or vice versa? Well, there's actually a pretty simple formula to do this, right? Since 360 degrees equals 2 pi radians, we can use 180 over pi and pi over 180 to convert to degrees and radians respectively. So if we're trying to convert 5 pi over 4 radians into degrees, what we're going to do is take our initial value, which here is 5 pi over 4 radians, and what we're going to do is we're going to multiply it by the formula that's going to put the thing we need on top, right? So if we have 5 pi over 4 radians and we're trying to convert it to degrees, we're going to do 180 degrees over pi radians. Remember, 180 degrees and pi radians are the same. So this would be like the same as saying like 2 over 2, right? And if that's the case, this just equals 1. So we can multiply it by 1 all day, right? It doesn't change anything. So what this is going to do is you'll notice that we have 5 pi over 4, and then we have 5 pi radians up top here. We have pi radians down here. We can eliminate the pi, and we can eliminate radians, right? And we're left with 5 times 180 degrees, and then 4 on the bottom, right? So that's what we have here. We go down, we have 5 times 180 degrees over 4, and if you do 5 times 180 divided by 4, you'll be left with 225 degrees. So in other words, 5 pi over 4 radians is 225 degrees. All right, so let's try one more. But in this case, we're going to... I'm trying to get this out of the way. It's just kind of annoying. Apparently not. Okay, so now we're going to convert 75 degrees into radians. So remember, we're going from degrees into radians. So now we need to have the radians on top. Remember, it's the same little piece here. We're doing 180 over pi. In this case, we're going to do pi over 180 because we want the radians on top, right? So what we can do is, first of all, we can cut the degrees. And then you'll notice that 75 and 180 both share a 5. So we can kind of reduce both of those. Just like before when you were doing fractions, if you reduce it now, it's probably a little easier than having huge numbers later. So if we divide both of these, we have 75 divided by 5, and then which will become 75 divided by 5 is 15, right? And then we have this divided by, oh, we're dividing each by 15. That's what it is. Okay. Sorry, I must have just wrote 1. There we go. Okay. So, yeah, so we'll get 5 here, right? And then here we divide by 15 and we'll get 12. So here we have 5 pi radians over 12, and that's what we end up with, right? So we took the 75 and reduced it. We took the 180 and reduced it both by 15. And then, of course, the degrees cancel on the top and the bottom, and that'll leave us with 5 pi radians over 12. So that is our answer. And we converted 75 degrees into this. Now, you can always, of course, in some situations, we can reference this chart here, right? Like if you know, oh, convert 240 degrees, right? Okay, 240 degrees is the same as 4 pi over 3, right? You can use this chart. It kind of gives you the answer. But if you ever need to convert something that's a little bit less common, you can just do it that way. All right, now to the fun stuff. Sine, cosine, and tangent in the unit circle. All right, so first of all, what is a unit circle? Well, a unit circle, the word unit is like a reference to the number 1, right? And a circle is a circle. So basically what we have here is we have a circle where no matter what, if you start at the origin and you go to the circle, you're going to have a radius of 1. That's what this is. So if we look here, I started off by generating this radius here. So we started off with this piece. And you'll notice that this is all called trig, right? Trig has to do with triangles. So we start off with this radius, right? And we just said that it always is a radius of 1, right? So that's this piece. Now, what we can do is we can create a triangle out of this, a right triangle actually, right? We can create a right triangle. We can say that the distance from this point, this new point up here, all the way down is y, because that's our y distance, right? It's our vertical distance. And then the distance from this point to this point is our x distance, right? Now, in this case, if I made this like 45 degrees, then x and y would be the same, yada, yada. You know what I mean? There's a bunch of rules with that. But essentially, the y is our horizontal, or the y is our vertical distance, and the x is our horizontal distance. Now, let's go ahead and go back to a phrase we used in trig quite often. It'll be still useful here. It's known as SOHCAHTOA, right? And this tells us about our trig functions. So we have sine, and sine, of course, is our opposite over our hypotenuse. We have cosine, which is adjacent over hypotenuse, and we have tangent, which is opposite over adjacent. Now, what's interesting is let's take a look at those with respect to theta, right? So if we have our sine, remember that sine is opposite over hypotenuse, right? Well, what is our sine in this case? It would be our opposite, which is y, over our hypotenuse, which is 1. So sine is y over 1, right? So sine theta is y over 1, which is y. So it's interesting that our sine function, or our sine ratio, is almost exclusively, and is exclusively tied to our y value. And then if we think of cosine, right? Our cosine is our adjacent over our hypotenuse, right? If we go down here, adjacent over hypotenuse, adjacent of theta would be x, hypotenuse is still 1, right? So this is going to be x over 1, which is just x. So our cosine is tied to our y value, or our sine is tied to our y value, our cosine is tied to our x value, right? And then tangent, this is kind of interesting, right? Our tangent is our opposite over our adjacent. So opposite is y, adjacent is x, our tangent is y over x. Another way of thinking about this, because remember how I just told you that y is associated with sine and x is associated with cosine? Well, for those of you noticing this, we can also think of this, and we'll get into this later, we can think of this as tan theta equals sine theta over cosine theta. And we'll get into all these trig identities, not even in this chapter. We'll be going into the next unit before we get into these in more detail, I should say. But you can see how this actually starts to play out, how we're actually starting to use these trigonometric ratios we had before and we're going to be able to start to do equations with them, or we're going to be able to do a bunch with them. And that's kind of this is the basis of trig. This is where all of trig comes from. So let's start off here. Let's find sine of 0, right? Find of 0 degrees. Well, remember, okay, so let's just do this. At 0 degrees, the values are x is 1 and y is 0, right? If we go up here, 0 degrees, remember, is this initial side, right? This is 0. You'll notice that at the end here, right, of 0, we have 1 comma 0. In other words, our x value is 1, our y value is 0. Well, what is sine tied to? Because remember, we're finding sine of 0. Well, the sine is tied to our y value. So what is our y value here? It's 0. So sine of 0 is 0, right? And in fact, if we go back all the way over here, right, and we look at our unit circle, right, you'll notice here we have a 0. So anytime we're talking about our sine value, and we look at all of these numbers here on the outside, all we have to do is reference. So what's sine of 120? Well, let's look at 120 degrees. What's our y value? Square root of 3 over 2. So sine of 120 is square root of 3 over 2. You can put it in your calculator to tell you that, right? It's just super neat. So, all right. So find sine, cosine, and tangent of 0 and 90 degrees. Well, let's talk about 0. 0 is the point 1 comma 0, right? At 0 degrees, we're at the point 1 comma 0 here. So let's think about that. 1 comma 0, our x value is 1, so our cosine will be 1, right? Our y value, we already just talked about that, is 0, so our y value is 0. Our tangent, right, is y over x, so it's 0 over 1, which is going to be 0, right? So if we go down here and look at it, right, sine of 0 is, of course, 0, because that's what our y value was. Cosine of 0 is actually 1, right? Cosine of 0 degrees is 1, because that's what our x value is there. And the tangent of 0 is 0 over 1, which is 0. Now, if we go to 90 degrees here, right, let's talk about 90 degrees. So remember, this is 0 here, right? So just to make sure, this here would be, like, if there was no other angle, right, this would just be 0. But now when we go up here, we create our 90 degree angle, right? So now we're talking about this point here specifically, right, on the unit circle. So you'll notice here, our x value at 90 degrees is 0, and our y value is 1. So now our sine is going to be 1, our cosine is going to be 0, and remember, tangent is y over x, so it's 1 over 0, right, which is going to be undefined, because anything over 0 is undefined. And if we go down here, right, when we go to solve it, this is what we put, right? Sine of 90 degrees is 1, because that's at the point 1 comma 0. It's literally like at the top of the circle, right? And then the cosine is where x is 0, so that's going to be a 0. And then tangent would be 1 over 0, which is undefined. Now, what I would strongly suggest that you do is, I mean, you can look off of this unit circle over here if you'd like, but if I were you, I would look at 180 degrees and 270 degrees and just see if you can find sine, cosine, and tangent of those as well. Because if you can start to get a feeling for how those work, it'll give you a nice head start on everything. All right, so this is just lesson 1, right? We're just kind of talking about the basics of what it even means to do trig, right? We're talking about what coordinate planes are, how we can read angles, what reference angles are, coterminal angles, right? We talked about a lot of things. So in review, we defined angles, negative angles, reference angles, and coterminal angles, and found them in the coordinate plane. And then we defined radians and converted between radians and degrees, and then evaluated sine, cosine, and tangent in the unit circle. All right, well, in the next lesson, we're going to actually do a little bit more evaluating of angles. We're going to do a little bit more math with this. But for now, we'll just kind of feel good about what we've learned here today, and I'll see you in the next video.